So welcome back to part 2 of our welded connections videos. As promised, we're going to go over a couple of different types of examples related to welding. In particular, we're going to look at just kind of a simple fillet weld calculation of base metal and the weld material itself. We'll look at the an eccentric weld connection situation, and then we'll also look at a scenario where we have fillet welds in a group that are made up of longitudinal and transverse welds, and we'll work through all of those examples today, just kind of give you some exposure to the different AISC requirements and methodologies of the 15th edition Manual of Steel Construction. All right, so the first one up is just going to be a simple basic fillet weld calculation, and what I have is I have basically two plates that we've set together here that are forming a T cross section. The top plate is going to be a 1.5 inch thick plate of A36, and the web or the stem is going to be a 5/16 inch A36 plate on the web. Now, we're not really worried about the width and the length and the dimensions of all of that, and I'll explain why here in a little bit. So the basic loading that we're looking on this is basically that the top plate is being pulled with some force V, and that the bottom plate is being pulled with some force V also. So the whole thing is in equilibrium, but we're transmitting this shear across that weld line, and that there are two welds happening here. Okay, so we're given that the electrode of this is an E70XX electrode, so that tells us that we have a 70 KSI electrode on our fillet weld. Okay, what we want to do is we want to find what's the maximum capacity of this weld. Now, notice I didn't give a length here, because what we're going to do is we're going to be writing this in some sort of kip per inch kind of calculation. All right, we're going to evaluate the welds in this arrangement with those units on it, and then we can back into how long a weld do we need if that's the kip per inch. And that's kind of a fairly standard practice of how we do this. Okay, so all right, so the solution for us is we need to look at and find a couple of deciding factors. The first one is always figuring out, well, what kind of weld are we looking at here? Okay, and so I've told you that it's a fillet weld, and it basically looks like a fillet weld. Okay, you might see a logo that looks something kind of like this, and maybe, since I don't know the thickness, let's just say that it's a weld that looks like that, and then there's one on the near side and one on the far side. That could be our basic logo for the weld, and that would also tell me that it's a fillet. I can tell you whatever type it is depending on what those characters are coming out of the symbology that we discussed in the last video. Okay, so that one's pretty obvious. Okay, the first thing we're going to do is that for this arrangement, okay, remember that there are parameters that affect the minimum size and the maximum size depending on the thickness of the plates that we're looking at. So I have one plate that's 1.5 inches thick, and I have another plate that's 5/16 of an inch thick. Okay, so the minimum size, we're going to pull that out of table J2.4, and it basically says that for, if I call the 5/16 plate the web here, that from this table, then for a 5/16 inch web plate, the minimum thickness is 1/8 of an inch. For the flange, the top piece, for 1.5 inch thick plate, the A minimum is 5/16 of an inch. All right, so if that's the case, then the minimum weld thickness that I can use on this assembly is 5/16 of an inch. Even though this guy was a whole lot less, it's 5/16. All right, and the reason is that these plates, as they get very, very thick, okay, and we talked about this in the last video, is that they get hard, they become harder to hold heat, okay, which is part of the welding process. So as I'm welding this thing, this guy will not heat up nearly as fast as the other plate, and so I can get kind of a weakness that it forms on this boundary. Okay, and so that's what AMIN is trying to accomplish, or trying to capture, is to make sure that you put a big enough weld on a plate that it's connecting to, so that it doesn't just experience some sort of cooling or thermal issues associated with it. All right, so that's my minimum on this. Okay, the maximum weld size was located in the text in the same section, J2, and then we're looking at item 2B. Okay, and so what it says is that for our plate T1, which was the 5/16 plate, okay, because of its size, being greater than 1/4 of an inch, the maximum weld size I can do is the thickness of the plate, okay, minus 1/16 of an inch. So that tells me that my maximum for that one is 1/4 of an inch. Okay, and then for T2, the 1.5" plate, the maximum is going to be 1 7/16. All right, so where we use the upper bound on the minimum, we use the lower bound on the maximum, right? Because what happens is this maximum weld size is to prevent us from going to the opposite problem that we had with the minimum, right? That if I put too big of a weld down compared to the connecting parts thickness, I don't burn a hole through it. And so, obviously if I put an 1 7/16 of weld, this is a monster weld anyway, but if I try to put that onto a plate that's 5/16 of an inch, I would burn through that plate more than likely. And so we want to make sure that that doesn't happen. And so that's why we're going to control the maximum as 1/4 of an inch. Now, if you notice, what happened based on these two plates is we have a problem that A max is greater than A min. Okay, and so this is an impossibility, all right? And so what that basically tells you is that the proposed connection that we're putting on these plates to put them together, this isn't optimal, and we're going to violate some of the AISC requirements. So what really needs to happen is we've got to resize the plates or reproportion them so that the welding works. And that's one of the difficulties that happens in welding that we don't necessarily face in the bolt calculations that we've done in some of the other videos. So for us, basically to sum this up, A min is 5/16, A max is 1/4. It's impossible, all right? So what we're going to do for the sake of this argument is we're going to resize the plates, okay? And so that will take us to the other half of this. So that's kind of I know it's kind of a gimmicky example, but this is one of the problems and one of the reasons you have to watch the A mins and the maxes is that it helps you proportion the plate sizes that go into a connection. All right, so instead of making them two different sizes, let's instead say that they're both the same and that they're both this 5/16. Okay, when I do that, then following the same logic that we just did for the previous example, A minimum is 1/8 of an inch, A maximum is 1/4 inch. Okay, this works. I can choose my actual A for this fillet weld that lives somewhere in between those. I could go 3/16, I could go 7/32 or whatever I wanted to do. But this is possible and this will work. All right, so if we want to get the maximum capacity out of it, obviously we're going to choose the upper end of this. And so I'm going to choose A equal to my A maximum of 1/4 of an inch. Okay, and that will be how we start to kind of size this. This will get us the highest strength for a given length of weld. Okay, so the next step that we do is we're going to figure out what the effective throat is, this TE characteristic that we talked about. All right, and so remember that for a fillet weld, we assume a triangle, we assume that it's 45 degrees. Okay, the dimension A that we just found is the side of the triangle, and this is 90 degrees, like that, okay? Then TE is the diagonal that comes across that, okay? And we said that TE is 0.707 times A. Again, this was the sine of 45 degrees, and then that's multiplied by A, and so that's where this 0.707 number comes from. And so we take 0.707, I multiply it by the 1/4 inch, which is my A value, and so my effective throat for a 1/4 inch weld is only 0.177 inches. It's a little less than 3/16. All right, so now that I have the weld figured out that I can put on this, now I can go in and I can start looking at the strength calculations. And so the first one that we're going to look at then is the actual base metal. So for our particular assembly, we're going to look, and because both plates are the same thickness, then this capacity will be the same for both plates. And so by our definition of these strength calculations, we're going to take FBM as being Fy, 36 KSI, and then the ABM, which is the area of the base metal, that's what the BM stands for, is actually the cross-sectional area across this plate. So if my plate was looking like this, and I'm putting a weld here and I'm putting a weld here, then the length that we're looking at, let's draw this kind of in a 3D ISO view, if you will. This weld is running down that length. The box that we're looking at is that cut that goes down the length of the weld, that cross-sectional area. All right, so we're going to have what is 5/16 of an inch here, and then we're going to go this direction. Oops. Some amount as length L, and we don't know how far we're going to go. And this is the reason that we're going to do all our calculations in kip per inch. So the cross-sectional area of ABM then is 5/16 times L. Okay, and so that's that area that's here. Okay, and then again, it runs the length of this for however long L is. Okay, and it's the same value for both plates. So once I have that, then I can figure out what the capacity of the base metal is under these two basic welds. All right. And so here we go. So we've got phi RN. Okay. So phi is 0.75. So that's phi. Here's the FBM value, 36. Here's the 5/16 L. And so the capacity of the base metal is then 8.4 times L measured in kips. Okay. Or if I divide everything by L on this, then that would be the same as saying how much load is it on 1 inch? Okay, well, it's 8.4 kips on 1 inch. So that's why we write it as 8.4 kips per inch. All right, and so that becomes a measure of how much weld I would need for the base metal in order to break these 5/16 inch plates. So then we can move on to our weld metal. And the formula that we showed you last time was phi RN is equal to 0.75 times the weld stress multiplied by the area of the weld that has to fail in order to break this thing apart. Now, our particular model, we said that we had 2 welds, one on each side of the plate. All right, so the FNW, as it's coming out, we said was 0.6 times the FEXX value. Okay, and so for fillet welds, this is 0.6 times 70 KSI, so 42 KSI, no major issues. Okay, and then the area of the weld that has to fracture, and again, if you think about this weld as being a triangular prism, and this is my critical section, then what happens is I have to fail it on that plane. So it's kind of that 45-degree plane that goes down the entire length of L. So that's all we're calculating, all right? So, again, we said that this distance was TE and then multiplied by L, and then we're off to the races. So the area of the weld then is TE times L. That's what we just said. And then I get this 2 because that's the number of welds there. All right. So if I plug in all of this information, I've got everything that I need. 0.707. Oops, I got to get a 2 in there. Left that off. Okay. 0.707, 0.25 inches times L. That gives me 0.354 times L. And then I can plug all of this into my capacity calculation. So again, once again, oops, keep breaking my lead. The phi is equal to 0.75. Here's the stress, and then here's that number that we calculated for the area of the weld. And so we get a value of 11.2 times L kips, which is the same thing as 11.2 kips per single inch. Right? And so then the capacity of this thing is the smaller of the two of these guys. So the smallest control, so we have, in this case, I had 8.4 on the base metal, and I had 11.2. So this is 8.4 kips per inch, and then this is, we could put a note that says that base metal controls. All right. And again, I apologize for the page drifting down, so let's try that again. So here's the 11.2, smallest controls, so forth. So base metal controls here. All right, and so that would be my capacity. Now, what we can do with that is let's just go in and say, supposing that we knew that V was equal to 100 kips in our picture. Because again, the picture that we drew on this was I'm pulling V this way, I'm pulling V this way, and we're welding with 2 fillet welds along this line. Okay, what we want to figure out is what's L? Okay, and if I do that, then we just found out that phi RN was equal to 8.4 kips per inch. So what we want is we want 8.4 kips per inch times L equals 100 kips. And if I run that out, L is going to be right around 12 inches. And we'll check my calculator just real quick to make sure. 100 enter 8.4 divide. Yeah, 11.9 is the actual number, right? So 11.9 inches there. So round that up to the nearest inch. And so if I put 12 inches of weld on both sides of these two plates together, I'll be able to hold that 100 kips. And so that's kind of how we start to kind of analyze the basic behavior of a fillet weld. All right. So that's the first example. The second example we're looking at then for us is we're looking for weld cases in which I have combined longitudinal and transverse fillet welds working together. Okay, and so I kind of drew a sketch of what it is that we're talking about. Is that I have some sort of object. It could be, a channel or an angle in which I weld the top, the end, and then the bottom in equal amounts. Okay, if you remember, if my axial load is pulling to the left on this, the longitudinal welds are parallel to the load, the transverse is across it. And so the thing that we have to remember is that this is for a concentrically loaded case, which means that this length and this length have to be the same. So that's concentrically loaded for what we're trying to do. And so when that happens, then there's a special provision in the specification. In this case, it's J2.4B, item number 2. I know it's way down in there, but it's there. And there are two formulas that says that when this happens and I have a concentrically loaded on the longitudinal and the transverse, then we can compute the capacity as follows. And we could do it the classical way of just taking the capacity of all the longitudinal welds and adding it to the capacity of the transverse weld. That's what these two quantities are. But there's also an interaction that happens as stresses get distributed a little unusually in this, that, because I've got the side tied off and the end tied off, this little corner back here may not be doing as much work as we had hoped. Or, if this is my stress, that the majority of the stress is wanting to go into the transverse weld as opposed to flaring out and going up to the longitudinal. So instead of being a uniform stress across this, it's actually kind of piled up kind of in the middle. And so what they do is the AISC recognizes that, and they say, all right, well, the other formula that you can check to make sure that you're okay is that, that you're at 85% of the longitudinal plus 50% or 150% of the transverse. And of those two calculations, you're going to choose the larger, okay, as your capacity, right? And so that's what we're going to do. So again, I have a little bit of an example here to kind of illustrate the way that we're going to work this out. For us, I've got a plate that's oriented. I'm pulling on that plate with some load P. In this case, the P is vertical. Now notice it's a different orientation than the picture that we had here because the longitudinal weld is related to the direction of the P, as is the transverse. So when I moved it vertically on here, we know that this is the transverse, okay, and this is the longitudinal, and that's the longitudinal, right? And so what we're doing is we're saying that the welds in this diagram, it's a fillet weld, it's 5/16 of an inch, and that's typical for all the welds on the diagram. And so what we've done is we've come in and said, all right, I've located P, it's at 5 inches, the length of the transverse is 10 inches, and then the length of the longitudinals are 8. Okay, and again, we're given that it's an E70 electrode for us to do that. Okay, and so like I say, orientation matters, so that's what this picture is kind of showing what we just had before, that the longitudinals are the sides, transverses across. Okay, and so what I want to do is I want to go in and I want to figure out, now instead of checking the max and the min, since we have no information about the plates and the base metal that's being connected on this, okay, we're just going to say that we know that the weld is 5/16 of an inch. That was given in the drawing. And so we find the effective throat, again, with that 0.707 number multiplied by the effective, by the weld size. That our effective throat then is 0.221. And then all I do is I basically plug in and calculate the capacity associated with my longitudinal weld, okay, plus my capacity associated with my transverse weld. And so when we go in on this, coming up with the capacity, so here's my 0.6, here's my FEXX, okay, and then I have 2 welds, so that's the number of welds, and then I have a length of 8 inches on each one, and then I'm going to multiply that by the effective throat of the longitudinal weld, and when I do that, we get just shy of 149 kips, 148.5. Okay, now, this does exclude terminations, because one of the factors that we haven't really talked about on really short welds is that in the process of laying down a weld of some length L, okay, when you first start the process, you get a lot of splattering and sputtering, and the first amount of weld at the end is generally not good quality, and so often you discount that, and that's generally related to the thickness of we discount a thickness out of the overall length. So again, we said the overall length is this. And then as you're coming off, so you start here and you start welding, and by the time you get to here, now the weld's good. Okay, and then as you get close to the end, your hand starts to lift up and you start to have kind of a similar problem on the back end. And so this is what we mean by terminations. Okay, the better welders can make this a very, very small number, but AISC says, always try to take a little bit off. But again, for what we're doing, I'm not worried about that. The L that you would be using then is that dimension. What is that guy? And that's all we're saying. So that's kind of what this termination is, that you'll see mentioned in time to time in the code for that. Okay. All right. So going in and looking at our RWT, which is the capacity of the transverse weld, okay, or the end weld coming in 0.6 FEXX. I have one of those welds. It's 10 inches long and it's 0.221 inches. So that's 92.8 kips associated with the end. Okay, now all I do is I plug into those two equations that we had up at the top. So the first equation was just the sum of those two values. So 148.5 plus 92.8 gets me 241.3 kips. All right, and then that modified one, the second equation was 0.85 of the longitudinal plus 1.5 of the transverse. And this number actually comes out as 265.4. And according to the specification, I can take that. All right, so even though this might be considered as a failure, if I load it with this is what it's capable of holding. All right, and so that's just kind of one of the specifications for concentrically loaded longitudinal and transverse fillet welds. All right, so our answer for this then is, again, we don't have a phi factor on this, so I take my phi RN, I add in phi, that's this guy, and I multiply it by my 265.4, and that gets me to 199 kips. So the capacity of this combined transverse and longitudinal fillet pattern is 199 kips. So again, it has to be concentric, and the length of this guy and the length of this guy have to be the same. So that will, and if I meet those criteria, then this extra little methodology will work for us as well. So that's another one that will pop up from time to time. This happens a lot in, like I say, connections with plates, and as well as connections with channels where I needed extra capacity. Okay, that I start welding here and I come down to the end, and then I turn the corner and weld some more, and then I turn around and come back up. So you will see those from time to time. So that's a kind of a good practice habit to get into. All right. The last one that we want to talk about then is eccentric shear and welds. We did this with bolts, and I showed you all an elastic vector method for computing for bolts. And while it wasn't hard, it was a little bit lengthy. And for welds, it gets even more complex. And they don't really have a true elastic vector method, though we can make a method that will give us a guess. But AISC has done a fabulous job of generating AISC tables for the eccentric shear. So if you remember, we had the bolt pattern tables last time. Well, the AISC tables for welds are very similar, okay? And these are located in Section 8 of the code, and I'll show you one here in just a second that is table 8.4 through 8.11. So let me get that open for us real quick. All right, so what I've done is I've gone in and I've just kind of arbitrarily chosen a page associated with, in this case, table 8.4. And what you see is that, like before, we've got kind of an arrangement of patterns. And in this case, what they have is I have an eccentric weld with a load that's at an angle of 75 degrees. And in this case, my weld consists of two vertical lines of weld having a length of L. All right. And in all of these, we have the same kind of parameters. We're going to define the eccentricity as coming from the center of the weld pattern out to where the load is acting. And we're going to call that as EX. And that's going to be equal to some value A multiplied by this parameter L. So it's kind of a percentage of the overall width is the way they've calibrated this. And likewise, the spacing between these two lines is K times L. So K is also a percentage of the total L. And you can see that the tables down below, when you get in there and you look, that I have a whole lot of K values and I have a whole lot of A values, and then it's just a matter of pulling off the value that I need out of the table. But one thing I do want to show you is, again, we've got to be very conscious of the load, this angle of the load. So in this case, it was 75 degrees, just having the table that I chose. But if we start kind of flipping back through here, you can see that some of the welds start changing. So now I've got two horizontal welds related to the load. And if I go a little bit further back, now I've got a box that goes all the way around. What I can't do is I can't take the horizontals and add it to the verticals. It doesn't work that way. You have to find the one that has all four if you have an all around, like say this is the end of a tube steel or end of a plate that you're trying to weld all the way around. Okay, and then here's a horizontal box. And then this one is the C shape, and this is probably the most common, where I have a plate that comes out to the end, and then I have a point load acting on the end of it. So this is the one, we'll have an example, we'll talk about this. And then there's some others. We kind of flip back through here. There's a whole bunch of tables. They've done a fantastic job on these. I have basically L-shaped welds, where I'm only welding two sides, and then what's the values associated with that. And I think that's pretty much all that we got. Yep, that's all we got. Okay, one other table to show you as we start to do this is table 8.3, okay? And this is an electrode strength coefficient C1 value, okay? And we'll be using this in the calculations when I show it to you on the other page. but basically it's for the strength of the electrode. And so they've got a lot of them listed here: 60, 70, 80, 90, 100, 110. And you'll notice that for an E70 electrode, my coefficient is 1.0. So this table is, the manual is calibrated for an E70 just because it's the most common. But if you have some other weld strengths, then you have to adjust the factors accordingly by the parameters in this table. And that's located up in 867. Again, 99% of the time it's a 70 KSI electrode, and I know it's 1.0, so this value doesn't even really matter, but just so you're aware of that one too. Okay, all right. So let's go in and we'll set this aside for just a second. And we'll get back to what we had here. So again, just so that you can kind of see a little bit closer up, what we're doing is that for centrally loaded weld groups, I showed you the different patterns and the different tables on there, but I wanted to talk a little bit about this one where the loads are parallel vertically, okay, because the same table can be used for two different cases. So again, I have two welds lines that are parallel. They have a length of L, top to bottom on this guy. Okay, they're separated by a distance KL, and the eccentricity of the load from the center point here is A times L. Okay, the table values that come out of this case are exactly the same as kind of an out-of-plane prying case in which I have these two lines of weld in one plane that's kind of heading off this direction. Okay, and then if I come out perpendicular from that direction and apply the load on the end of that at a distance of A times L, it's the exact same scenario. Okay, so what I kind of tried to do, and the picture's not totally obvious in the AISC manual, it's a little hard to deduce, but you'll notice a couple of changes on this one. One is that any distance will work on this. For where it was KL before, now it can be any distance. And then if I look at this from the side, this is kind of the arrangement of what we have. I have a weld, and then a distance into the page is another L weld. So they're all on the same line, and then this is the guy that's happening in that perpendicular plane to the plane of the welds. So just be kind of advised that. But again, we've kind of talked about A's and K's and all that kind of stuff, and I'll show you the example to try to deduce that as well. Okay, so just like before with the bolts, the formula is really, really simple. Okay, that the capacity of this group, which means the load that can be applied, is phi times C times that C1 correction factor for electrodes that I showed you, times the variable D times L, which is the characteristic length of the weld pattern that you're looking at. All right, so going through these things really quickly. Again, phi is 0.75, C1 is 1.0 for the 70 KSI electrode. That's table 8-3. Okay, and then D is the number of 1/16 of an inch increments given on the weld size. All right, which basically means that a 1/4 inch weld, D is 4, because that's 4/16. And then a 1/2 inch weld is 8 or 8/16. So that's the only real trick, is you got to remember it's the number of 1/16 portions. Okay, and then C is the coefficient, and this comes out of the table that we're looking at. Really, really simple. Okay, all right. So before we get into a numerical example, again, I kind of just illustrated the different sections that are possible in the tables, and I showed you this when I flipped through the book, but again, table 8.4 is dealing with loads that are vertical, or welds that are two welds that are vertical. Table 8.5, two welds that are horizontal. 8.6 and 8.7 is the box pattern, and then 8.8 is the C channel, and then 8, 9, 10, and 11 were all the ones that look kind of like this. Okay, so it doesn't matter. Make sure you get into the right table, and then once you're in that table, make sure you get the right set of figures that correspond to the angle of the theta that we want, because that's what helps us to try to tally up our particular table. All right, so let's give one a shot really, really quickly. Okay, so here's our example. I've chosen to choose a C shape as my weld pattern, okay? And the way that this is defined is that the centroid is here. And again, you can only do welds in which this leg and this leg are exactly the same. All right, so my L, the height of the weld pattern is given as 10 inches. I have an 8-inch eccentricity out to my load. And then we say that my load is inclined an angle of 30 degrees off of the vertical. And so when I do this, and we go in and, I missed one. Oh, the 6-inch, yeah. The length of this weld is 6 inches. Okay, and then we've got our weld symbology that basically says that all three of these guys are 5/16 inch fillets of E70 XX electrodes. Now, and so that should be fairly clear what we're doing, and that's kind of how we can denote all the weld symbology. for this. All right, so the data that we can collect from this parameter is that we know that the L characteristic is 10. Okay, the eccentricity we said was equal to A times L, and we were given that that was 8 inches. So A times L is 8 inches, tells me that A is 0.8 inches. All right, and then KL, which was the length of this extension, if you will, KL is 6 inches, so that means that K is 0.6. We were given that it's a 5/16 weld, so D is 5, and then C1 is 1.0 because, again, we're dealing with a 70 KSI electrode out of that table there. All right, so all we do then is once we find our right table, okay, and so the table that we want for this scenario with the 30 degrees is table 8.8 on page 8-94. And what we're going to do is on this axis is A, on this axis is K. I'm going to basically look for the intersection of those two values that we looked up. So my A is 0.8, my K is 0.6. I'm going to come down and I'm going to read this 2.50 number. And that's the value of C in the equation. So if you look at it, just so we can prove it, for the 30-inch table, this is the one that we want. Okay, so this is the characteristic that I want. So if I go and I do my A, we're coming down to, what was A? A was 0.8, 0.8, so that's going to be this line here. And I'm going to read over to 0.6, and you can see that's where 2.5 was showing up. Okay, and that's all there is to it. Piece of cake. Okay, so really, really fast and really, really simple to do once you understand what each of the characteristics are. Again, look at the picture that's up at the top of the page, and it will help you out as well. So now all I do is plug and chug. Phi RN is phi times C times C1 times D times L. So here's phi, here's C. My C1 was 1.0, my D was 5/16, and then my L, my characteristic length, was 10 inches. And what that tells you is it tells you that the capacity of all of this is 93.75 kips. All right, so what that means is that I can put a load of almost 94 kips inclined at 30 degrees at that eccentricity on this weld pattern, and it will pass the AISC specification. Super, super easy. So like I say, all you have to do is make sure you get in the right tables with the right angle, and you're basically home free at that point as long as you can identify the parts. Really, really, really simple. So, all right. So for now, for us, that pretty much sums up some of the examples that I wanted to kind of show you on how to deal with welds, especially regarding, the weld strength and the base metal strength, as well as our eccentrics, as well as those combination cases for fillet welds that have transverse and longitudinal welds. So I hope it's made sense to you. As always, if you'll leave us some comments down below, let us know if it was clear, or if not, what we could do to help improve it, because we're always evolving these lessons. Otherwise, toss us a like for the video if you enjoyed it, and then please be sure to subscribe to our channel, and we will keep the videos coming. And with that, I bid you a fond farewell and a good evening. Happy engineering. Thanks.